All right, guys. Thanks for coming. Today we're going to talk about aviation grade command and control systems for beyond visual line of sight operations. My name is Christian Ramsey. I'm president of Avionics. We've got a couple slides, an introduction of who we are as a company. We're a U.S.-based avionics manufacturer primarily. We focus on communications, navigations, and surveillance equipment. So all of the systems on board a drone or even a manned aircraft that control the aircraft, communicate with the aircraft. A large product suite across multiple sort of verticals. We've got a unmanned or uncrewed aviation profile where we've got transponders, command and control radios, GPSs, autopilots, even some defense products in there. In manned aviation, we've got very popular in the US anyway, ADS-B out systems that are used for general aviation aircraft. And here in the UK, we have a very popular product called the Sky Echo, which is a portable electronic conspicuity device for general aviation pilots. Also some cockpit displays. And more of the topic of today is going to fall under the infrastructure and services component, where you can imagine that on the ground, there's infrastructure installed to enable crewed and uncrewed aviation, and specifically command and control for the discussion for today. We've got a number of FAA certifications, whether they're TSOs or STCs or even defense certifications, and I say that only to sort of lend some credibility to some of the things we're going to talk about in the next few slides. I'm going to go through a little bit of a case study here of what not to do from a command and control perspective. This is from an AAIB bulletin a couple of years ago. And the particular aircraft that was involved in this accident was an Lauda airspeeder aircraft. I have no personal knowledge of this event. Everything I've going through is from the AAIB report. I may get some of the details wrong if any of you happen to know what happened. This happened down in Goodwood. It was a large aircraft, 95 kilograms. It was taking place as a part of a demonstration at the Goodwood Festival of Speed. And there were about 35,000 attendees just about a mile away from where this accident occurred. It did go through an operational safety case effort. And this was a 3/4 scale of what is planned to be effectively a racing drone with a man on board. From a control system design, C2 system, they were using public spectrum, 915 megahertz. The transmitter indicated signal strength on board. They had two transmitters. It has a separate emergency power switch to kill the connection or kill the motors if something goes wrong. And from a lost link perspective, the concept was that the aircraft will level out and continue on its current course if the C2 link is lost. It did not have a GPS on board, so it could not hold its position or return home. It was just going to level out and hopefully recover the link in order to bring it back home. Shortly after takeoff, and this was being demonstrated at Goodwood with about 200 spectators, shortly after takeoff, the pilot realized that they did not have control of the aircraft and called for the kill switch to be activated. Didn't work. Kill switch didn't work. The aircraft began an uncommanded climb up to about 8,000 feet. And right above this airport is a hold pattern for Gatwick. So it hovered at 8,000 feet in a hold pattern for Gatwick for about 4.5 minutes until the battery died, and then it fell to the earth. Luckily, no one was injured, but this is a little diagram of where the event happened. So right here in the center is the demonstration capability. Up to the north about a mile is where the audience of the Goodwood Festival of Speed were, so about 35,000 folks up here, and the crash site was about roughly a mile to the south. So the only thing that saved that 95 kilogram drone from crashing onto a crowd of 35,000 people was the wind direction that day. So lucky. The AAIB report took a look at several factors, and there was a lot of things that went wrong. Going to focus only on the command and control pieces. Poor build quality, hobbyist components. The large amounts of solder and adhesive and electronic prototyping boards, very poorly constructed, very dangerous for an aircraft vehicle of that size. All assemblies failed a test against standards for IPC A610. AAIB commissioned an analysis of everything. There are 3 classes of devices under A610. Class 1 would be the lowest level, Class 2, Class 3. They indicated that Class 3 would be appropriate for this type of aircraft. It didn't pass Class 1. And the kill switch was a one-way comms only system, which obviously didn't work. Other things that went wrong, they used the public spectrum 915 megahertz. That in itself is not necessarily unsafe. There are mitigations for that. But you've got to have those mitigations in place. There was some transmitter range confusion in the documentation for the transmitter they were using. Some documents said it was a 40-kilometer range. Some documents said it was a 10-kilometer range. But there was unsure, and partly because the transmitter itself was configurable. We could select which frequency and which power, and effectively what came down to is they selected the wrong frequency and power for their particular operation that day. On their test flights, they used a configuration that was 100 times stronger and on a different frequency than the demo day. So they were transmitting with a very low power signal on 915 megahertz. And that wasn't even a compliant frequency. Within Ofcom, that is 0.1 megahertz away from the O2 network here, right? So so that is not allowed to be used in an airborne use. They should have been using 868 if they were going to use the public spectrum. The second transmitter, they forgot. No consistent monitoring of the connectivity, even though that transmitter had capability on there. The pilot was most likely looking at the aircraft and not necessarily looking at the signal strength on this transmitter, and several single points of failure in the design of the aircraft. So this is what not to do. Again, it's not an isolated case. The UK CAA set up a website called Drones Reunited. There's up to 26% of drones. Really, these are the hobbyist drones get lost because there's a flyaway scenario. Enough that the CAA has to set up a website. So how not to have your own AAIB report. I'm going to go through these in a little more detail. Take a look at your frequency selection. It matters. It's important what frequency you choose. 2, radio selection. It's not magic. These things work. It's engineering. And 3, network design. So in frequency selection, there's a few basics. You don't need to be an RF engineer, but you need to understand that low frequencies at a given power output travel farther than high frequencies, but they carry less data. They have less bandwidth. High frequencies can carry more data, but they're less range. Risk versus cost. This is one thing that is not well understood. There's a continuum over there on the right side of the slide that shows if I'm using public spectrum, I'm expected to accept more risk of interference. If I'm got a certified system using aviation spectrum that's allocated for a specific purpose, I can expect less interference, but I'm going to pay a lot more for it. So there's a continuum of cost and risk depending on which frequency you're going to use. Right in the middle is sort of the LTE SATCOM model, right? Where you've got a system that has some protected spectrum, and therefore you should expect that there's less risk there, but you pay a little bit more. So mitigations. So I mentioned that using the public spectrum is not necessarily a bad thing as long as you have loss link procedures and other mechanisms that can mitigate for that. Autonomy is a good mitigator in terms of what's my loss link procedures? Is it going to return home, return to base if I lose that link? How is it going to do that? What altitude will it do that? These are acceptable terms, from CAAs and FAAs around the world of ways to mitigate for use of public spectrum. And then legal. is it legal to use the frequency and the radio that I've chosen? Does it have an FCC in the United States? Does it have an FCC mark? Is the frequency, do I have a license for that frequency? Or do I have a license for that frequency at that power? Because they're not the only radio that has configurability selection. So you might go into a setting and say, oh yeah, of course I'm going to max out the power. Well, depending on the country or the region you're operating in, it's not legal to do that. And you're creating interference for others in the area when you do that. Radio selection, things you need to think about. Price, of course, they range from $100 to $10,000, or more, right? There's a huge cost range, and a lot of what goes into that price range is certifiability, quality of build, and frequencies that they operate on. Transmit power and receiver sensitivity translates to range. The appropriate bandwidth. You might be selecting something because it looks like it has the best spec from a bandwidth range, but if you don't need that much bandwidth, you might be sacrificing range for that. Size, weight, and power, compatibility with existing systems that are out in the field, interoperability with other systems that are on your aircraft. What's your EMI, electromagnetic interference position on your current aircraft? We've had to help many customers debug the wiring of their own aircraft due to poor wiring practices or bad connectors in their own aircraft. Again, legal, markings, accreditation, certifications of the radios. What are you looking for? Diversity. Do you want more than one radio on your aircraft? If you want more than one radio of your aircraft, do you want two different frequencies? So if one frequency gets interference, do you want the other frequency? How are you going to integrate those capabilities? Will it help you meet your safety case and understand the settings of the radio? From a network perspective, point-to-point systems are situations where what I call a point-to-point is where I've got one ground radio and one airborne radio, and that's a point-to-point system. There are obviously lots of applications for point-to-point systems. You can get great range even beyond visual line of sight with point-to-point systems. But the future of long-range operations over distances, surveying, linear infrastructure, delivering packages, et cetera, there's going to be some sort of network involved. And my simple definition of network from this perspective is more than two radios. More than two radios on the ground specifically is what we're talking about today. So examples of that: cellular networks, SATCOM networks, mesh repeaters, purpose-built terrestrial, which we'll get into a little bit, or combinations of the above. These are the networks that will come into play. So now I'm going to transition a little bit to talk about what Avionics is working on and how we're working to improve these solutions. So we have significant research and development focused on beyond visual line of sight C2 applications. And we focus on a couple of tenets. One, aviation grade radios. We have radios that are, we don't have a C2 radio that is currently TSO certified, and that's because the TSO is being updated to it. And so by this time next year, I hope to be speaking here about our TSO certified radio in C-band. Operations on multiple frequencies. So we want to give our customers the option to use multiple frequencies from the same aircraft. We've got an investment involved in that. Operations on purpose-built and commercially available networks. So we've got a couple of examples that I'll show here later where we are building out the ground infrastructure for a customer for beyond visual line of sight applications, and they would like to use those existing networks also with commercially available networks, i.e. LTE, as a component of that. And stay safety case focused. Stay focused on the mission, which is enabling our customers to fly, not necessarily capturing all of their payload data and streaming their live data or streaming the video. That's something that we might address at some point in the future, but today we're focused on getting our customers to fly safely. So the system we have is called Skyline. Skyline is on demonstration. If you take a look at we've got a booth about halfway down the hall on the right, down this hallway. And it's concept is a cloud-based, scalable, trusted network. So if we take one TSO certified radio and put it on the ground, and we take a second one and put it 20 miles away, we now have a network, and we have to coordinate that network. And we coordinate that network with a cloud-based system called Skyline. So all of our radios are network enabled. They phone home into our cloud-based service, and the cloud-based service, Skyline, manages all of that system. It's something like a UTM, but it is very focused only on the command and control portion of a UTM. So we call that a command control communications service provider, or C2CSP. That's a function that we are providing. So it supports network operations, both on ISM, C-band, which is a protected spectrum in aviation, and an LTE. So if you're using one of those three types of radios that we provide, you can bring all of that Skyline information into the system. The system enables multiple UAS to operate over that network. It monitors the signal strength and capabilities of the ground-based radios, the airborne radios, and the interactions between them. And it brings that all together into a managed system, saves all of the data, and keeps everything sort of in a managed perspective. One of my previous roles was I managed the rollout of the ADSB network in the US. I was a program manager on that program. So this concept of aviation grade ground-based networks is very much known to me, right? And so wanted to take this concept into building out that network for command and control. The other thing that it does is really important is seamless handoffs in what's called a make before break scenario. So if you are transitioning from Tower A to Tower B, and you have to release your connection to Tower A in order to reach over and grab Tower B, you're technically in a lost link scenario for that nanosecond or millisecond or seconds, right? You don't want to do that. That's not going to pass the safety case. So each of our radios is actually two radios. It's a redundant solution on board. There's two antennas. One radio remains connected to Tower A, while Tower B connection is established before releasing Tower B. So that's what make before break means. Some of our main customers and use cases tend to be infrastructure and network operators. We've got one customer that is a statewide operator that wants to build out a network that enables the entire state to bring commerce to the state, largely for the oil and gas industry currently. And they want to enable that network through investment funds through the state to build the network out, and then onboard operators. That's called the Vantis network in North Dakota. I'll talk about that a little bit. Enterprise fleet operators. If you're operating a fleet that is delivering a long-range cargo, et cetera, you want to fly multiple aircraft over a long range, these types of customers exist as well. We've got a utility company that's a customer of ours that are doing something very similar to that. These are really demanding customers that have invested heavily in their own internal UAS operations in order to realize a business case. In many cases, these customers are operating visual line of sight only today and are moving toward a beyond visual line of sight capability. And then drone OEMs who are seeking type certification of supporting enterprise customers. So the aircraft manufacturers who are seeking those type certifications or have to prove their credibility or their safety cases either in a standalone way or with their customer. So you do this through performance standards. You always start with the standard if you want to certify something. There are three key standards that we use on the C2 side. There's an ASTM standard, which is a basic, here's how you build a decent hardware, a hardware platform for command and control. It's mostly focused on connectors, vibration vibration tolerance, EMI tolerance, good sound electrical design. It does not get into specifics of frequencies or waveforms, but it's effectively best practices for building a radio that's going to go on our UAS. RTCA's DO362A is a specification for a C-band radio that's going to be the basis of the next version of that TSO. And that's a C-band radio, which is a globally allocated frequency for command and control, command and non-payload control of of UAS operations globally. So this frequency band is going to be accepted worldwide through aviation authorities. And this spec tells you how to build a radio, but it doesn't tell you how to build a network. In order to learn how to build a network, the DO 377A document is the best guide we have, which is called the MASPs, or the Minimum Aviation, is it on there? Minimum Aviation System Performance Standards, there you go. So that's how you take a system of systems and create best practices for building a network. So our Skyline network is built to the guidelines provided by MASPs. So if we go forward and go through certification processes like we are in North Dakota, it's the MASPs that will be used to do that. Just a quick screenshot of what the Skyline platform is showing. So here it's a little hard to see, but there's a green dot here that indicates a ground radio over here. There's another green dot here that indicates a ground radio here, and then there's another one at the end of this red line off to the north. So this represents 3 radios that are installed in physical locations in Montana. And we've got our drone flying, which is the blue diamond here. And you can see lines connecting to each of the 3 radios, because the drone is talking to all 3 of them at the same time. But the system has selected this one over here as the primary command and control at the moment. And I can see that, and there's a live demo that you can come see at our booth afterwards, because there's a little animation showing a 2-way bidirectional system. Over on the left, there's a bunch of radio stats that you can see. So we can see transmit and receive packets on both radios for both the ground and the air, number of satellites the GPS is receiving, the RSSI signal strength. Excuse me. So this is, the system monitors and records all of that data, which can be used later for safety case analysis. The system also can integrate external surveillance sources. So if you've got ADS-B receivers or an external radar or anything else from a detect and avoid perspective, that can be displayed here as well in terms of overlaid on there. The real-world example is Vantas. I mentioned it a few times. So this is a state-provided infrastructure for command and control, UTM, and detect and avoid. Basically, they invest heavily in bringing industries into their state, and they see UAS as an industry that they want to attract, not as a manufacturer, but users of that industry. They've got a lot of oil and gas customers there. They've got lots of highway systems over long ranges in rural areas with not a huge population density, and they want to enable unmanned systems operators to deliver goods, inspect infrastructure, et cetera. So they're investing, just like this is coming from the Department of Transportation. The same folks that build the roads are building this highway in the sky, as they call it. And we are what's called the Communications Service Provider, the C2CSP, of the Vantas towers. It's a performance-based network. We're going through what's called a 91-113 waiver right now, which is the BVLOS waiver with our own aircraft flying our own systems on this network. And the idea is that we are going to be paving the way for other operators behind us to follow the same recipe into the system and replicate success. A couple of examples of our radios that are installed on some of the towers. So these are 400 feet up on large Department of Transportation towers. What those look like. We do extensive performance testing. So this particular flight is a Cessna. We actually put our radios on a Cessna 182 and flew concentric circles in increasing range from the tower location to monitor the signal strength. And you can see through simple color coding of signal strength, with green being good and yellow being slightly less good, that there's probably some sort of issue with blocking right here. You can see this wedge introduced into the circular pattern. And so we fly this both with manned aircraft and unmanned aircraft. Every tower that gets installed has to get qualified and the performance quantified in terms of how this network is performing in any given location. And the pink overlay is the modeled performance. So the modeled performance is what we should see, and so we can compare our models against how good the actual performance is. The aircraft in the lower right is our test aircraft. That's the one we're working on our BVLOS waiver for. That's something. Oops. Two more. So one thing that's very important is dynamic frequency management. And this is specific to the C-band system. So C-band allocates 5030 to 5091 for UAS command and control. And there isn't enough spectrum to simply let everyone use that spectrum without some serving out of particular frequencies. So there's a dynamic frequency management concept that uses a frequency manager as an organization that, as a part of your filing of your UTM flight plan, you're going to file a flight plan and you're going to say, I'm going to operate in this area. You will be given a frequency for that operation that is deconflicted from any other operation in your region. So we're now deconflicting from aircraft, but we're also deconflicting from interference through the use of the frequency management organization. The frequency manager will take a look at the frequencies in use, frequencies that are planned to be in use for future planned filed flight plans, and you may get denied. There may not be a frequency available for another 10 minutes until the aircraft leaves the area, and you're issued effectively a hold. That frequency manager is being built into our Skyline under an FAA contract right now. So we're building this frequency manager corporation, and when you're issued that frequency, it already programs the ground radio to operate and communicate with you on that new frequency. So it's a seamless assignment that comes through your platform. This is just kind of a wrap-up slide, just talking about some of the things that we do that support your operations and support your certifiable solutions. And Skyline was one of them, but we also have TSO certified GPS systems, ADSP systems, both for manned and unmanned aircraft. We follow all of the DO-260 power requirements. We look at DO-178, DO-254, design assurance. Everything that is built into our culture of certifying avionics goes into everything we do, including the cloud-based systems that we've built. So this is a really key component and differentiator for you avionics and for you as our customers, to integrate those capabilities. And that's the end of my presentation.